We'll be talking about some internals of React, as you might have guessed from the title. So we'll see a lot about fibers and other cool concepts, some CS concepts. I am Matheus. This is me. You can find me as White Combinator pretty much everywhere on the internet. And I currently work doing front end at a company called Medallia, and I also mentor front end students at Tech Labs Berlin. And just like the other one, we got some disclaimers before we start. And we'll be talking a lot about the source of React and what's happening under the hood. And the source of React is something that's changing like a lot over time. So some of the things you're gonna see here are kind of speculations. And the second thing is we're gonna be diving deep into some topics. So yeah, whenever it feels like weird or something, we can always have discussions after the session, etc. So a bit of context on the why for this session and why I'm here and why I like this topic. So my history with those germs started back in 2020 when a friend of mine who was building a Bubble plugin to support his proposal to bring algebraic effects into JavaScript, and he basically asked me for feedback. And when I was going through that, I saw a lot of words that I didn't know a lot about them. So I saw coroutines, fibers, continuations, algebraic effects, and etc. And even though I didn't know a lot about these words, I had seen some of them before in React. And that made me feel a bit bad because I was like, I'm doing React for a living and I have no idea what some of these are all about. So that's the whole idea of the session is to put them like not only in the order that makes sense, but so that you can see how they all piece together and what would be the relation with React. Just so that I have more context about you. So who's here doing React or has done in the past or anything React-wise? Well, yeah, most of you actually. So the first thing we're gonna be talking about today are fibers. So the way I like to see fibers or the way I like to introduce them is to actually we start thinking about stack frames. And to think about stack frames, I have this really simple example. It's an add function. It's got two parameters. I'm creating local variables inside this function. I'll return my result, and in the end, I invoke this function. And if we were to model the stack frame in JavaScript for that, we would have something like this. So we have the return, we have the function itself, we got parameters, and we got local variables. And if we try to do a similar exercise, but with a React component, we would get to this similar result that we call a fiber. And we would have a return, but instead of the function, we would have the component. Instead of parameters, we have props. And instead of the local variables, we got the local state of our component. So that's the definition we'll state for now. So a fiber itself is this stack frame for a given React component. And what we call in the React realm fiber architecture is this specific implementation to React that mimics a call stack of a call stack in where React has full control of scheduling, and we'll see how important that is. So now we can start thinking about fibers as units of work. And let's recap a bit what happens with our components. So first, we write our JSX templates and etc. So once this goes through the compiler, we end up with a bunch of elements. So, or what in the past we would do, like React.create elements. And then we have the reconciliation phase. And during reconciliation, we have what's returned from the return methods or whatever, if that's a function. We have all these merged into a tree of fiber nodes. And of course, depending on the type of the component, under the hood, React has to perform different work. So if you have a function component or a class component or a suspense component or a profiler and so on, under the hood, the work that React has to do is different. And that's why each element is going to be converted into a fiber node that is going to describe exactly what kind of work needs to be done. And that's when we get to this one abstraction that is, we have a fiber as a unit of work. And because it's a unit, it's really atomic. That's what makes it a convenient way, for example, to pause, to schedule, to abort, or do anything with that work unit. Now that we can think about them as units of work, we can also think of visualizing that to make it like more clear. So for this, I got one experiment. So let's inspect some elements. So here I have this really simple app. I just have some local state that I increment and decrement, and I'm rendering that to the screen, etc. And if we start inspecting the fibers in there, and I know it's difficult to read. So the focus here is just that you see a lot of metadata that we have inside a fiber. So we have, for example, information about props, about state, about what's memoized, about what's not, about children, siblings, and yeah, like a lot of metadata. And we can use this metadata. So for example, let's say we come up with this code that's like just I have a regular JavaScript map, and I have this while loop that I'm iterating, and I'm adding those fibers, the fibers I found to this map I had. And here we can highlight some things that I'm using. So for example, I'm checking the child property out of the ones I saw. I'm checking for siblings and some other information. So, and by the way, that's only a really tiny part of all we can do. So here I'm gonna paste that code into developer tools, and I have a regular React app Twitter open. So I just created our map, so you can see, for example, we have like more than 3,000 fibers, almost 4,000 actually. And what I'm gonna do next is I'm going to select any element that I think that can be a component. So I click the follow button, for example, and I just selected that so that I can access with the $0 0. And what I'm gonna do now is that I'm gonna access my map, so I can do fibersmap.get, and I'm gonna pass this current element there. And that's when, for example, we can see, so we're gonna see information like what's this element. We see it's a div, but also everything we discussed. So which props, the next state, siblings, and etc. So that's the metadata we have about a component. And by the way, if you're interested in figuring out all of these properties, I would recommend that you check the source of React Reconciler. Especially this file, you get like a full documentation of what every property is. And another really interesting part is the work tags also inside the reconciler, because this file is actually what describes all the possible kinds of work that React can do. And that's also a really good way to track the evolution of the framework, because I myself, every time I check this file, I got like a different number. So last time I checked, it was like 25 different possibilities, but years ago it was less, for example. Now that we can abstract them and visualize them as units of work, another thing we can do is to manipulate them. For the next exercise, I do have a question. Who here has heard about this weird word, homoconstity? Okay, cool. That works better when no one has. So for this exercise, I have one example in Clojure, but if you don't have experience with Clojure, that's fine, because it's actually really simple. All we are doing here is we are binding x to the value of 1, and then next we are just incrementing so that we can get 2. So nothing too complicated. But what's special about this code is that we can think of this code as a list of 3 different elements. So first we have our symbol, there's named let, and then we have a list, we have a vector and a list with 2 elements each. And if we span these, we're gonna get a symbol that is x and an integer. And the same thing for all these. So we have a symbol that is the increment thing, and we have another symbol that is x. And if you think, it might sound a lot like I'm expanding the AST of that. And actually, you're right. That's pretty much what homoconstity is about. So I got this definition on Wikipedia, so I can read that. So it's a property of some programming languages in which the code used to express a program is written using the data structures of that language. So basically, it's like the code rewrite. It is really close to the AST of the language, or abstract syntax tree of the language itself. And the reason why I'm saying this is because we just saw that React elements are just data. So just like we do in Lisp or closure or any other language that has this property, we can think about getting this data and manipulating our elements. And this takes us to the second experiment, that is, let's talk about pattern matching. So who here is familiar with pattern matching? Maybe you've used some languages that has like Haskell or Elixir or some of them. So yeah, another cool definition. So basically, it's pattern matching is about specifying patterns to which the data you have should conform to, and then you check that to see if it does, and then if you can also deconstruct the data based on those patterns and etc. I know the definition is a bit abstract, but we can visualize that with an example. So this is a simple factorial function in Haskell, and first line we have the type annotation, and then the other two lines are the patterns we have. So we are matching for first there is 0 and what should happen, and then we are matching our general case. And we can have more complex stuff, like we can have different cases, and those examples are really simple. So this is like the Fibonacci one, where we have two base cases, and then we have like our recursion case. And again, why I'm showing you this is because we can start thinking of some similar abstraction in React. So in this code, what I have is a hook that is basically performing an API call, and then I have these three components, match, with, and otherwise. And what I'm doing is, via props, I am matching the shape of the return of my API call. So for example, if that's an error, I'm rendering the error message. But if that's okay, and I got a text, like my data is a text, I render the text. And that if that's an image, I render the image. And basically, I'm matching against the shape of the object. So, and it's fully typed, as you see. So this is really, really powerful. And the source of some of these components, it looks like this. For example, this is the source of is when, that is what I have inside the when component. But the key thing I want to show you is, for example, that this is possible because I can check the type of my element, or because I have utilities from React like children to array that allows me to go through all of these elements and get information about them. This kind of thing empowers really interesting stuff. So in this second example, I'm basically rendering different things if the browser supports or not some feature, and I'm wrapping that with suspense, and I'm using React.lazy. So what we get here is the pattern matching thing with suspense in React.lazy, and in the end we have our users downloading only the actual bundle that matches a given condition, or in this case it is a predicate function, but it could be a specific shape as from the previous example, and all of that because we can reflect about the elements data. By the way, if you want to check it out, it's on GitHub, but it's just get the idea, don't use that in production. And to recap a bit, so with fibers, React can pause, resume, restart any rendering work on components, and can also reuse previously done work, which is an amazing optimization. And it can split work into these fibers chunks that we saw, and because they are different parts of the work, you can have like different priorities, and that's what Concurrent React is pretty much about, by the way. And before we move to another thing, it's really important to mention that fibers is not like a React concept actually, and it's just a generic model for where we have like work units working in cooperation, and actually operating systems use fibers under the hood, and even some programming languages like OCaml, they also have fibers as like a citizen language. And not only that, but there are other libraries in the JavaScript realm, like Effect.ts, that aims to bring like fibers and similar abstractions to the work, to the JavaScript work. So the next one we have are coroutines. And my journey with coroutines started after this tweet by Andrew Clark. He's one of the core maintainers of React. And he said that suspense would trick people into learning about coroutines. So I followed his tweet. And I started digging about some definitions for coroutines. And the first one I saw is that it's a generator, or a producer that can also consume values. So it's like, okay, the generators we have in JavaScript, they can consume values. So by this definition, they would be coroutines. The second definition I found is that it's a generator that can resolve async values like async await. And who here has done like promises in JavaScript before we had promises? Cool. So this is also pretty familiar definition in the JavaScript world. Before we had promises, we had things like call or even the Bluebird set of utilities that under the hood they were doing generators. And not only that, but Babel, for example, when implementing support for async await, it was also doing generator functions. And last but not least, I found this one that's probably the fanciest one with nice words, that it's a generator that can yield with the stackful continuation. And we'll talk about there in a minute. But for now, let's abstract as we had deep async await at different depths in our structure. And we can think about that with suspense, for example, because we can pause reconciliation at any depth of our component tree. So just to recap before we move forward, with fibers, we have the control passed to a scheduler, and this scheduler is what's gonna say what's running next. And this might happen at framework level, OS level. It could be, for example, Node.js event loop itself. And in coroutines, we have the control passed by the caller, and that's handled by application code. So it's you who's writing the code that handles that. And so what's the relation with React? Actually, it started like first when they were thinking of fiber as a specific component type. So fibers were like the big thing in React in 2016 or 2017, for example. They were the big thing before hooks, and actually the whole idea of fibers was to empower hooks and concurrent features in React. But back then, when they were modeling the whole thing, they had even two component types. They had coroutine component and yield component. That's, by the way, the ones that, this is the same file we saw in the beginning where you have the different component types. And the idea back then was actually to give explicit control over yielding and resumption of the work. And by the way, that's a pretty interesting PR if you want to check it out. I definitely recommend you to. But the thing is that back then they stumbled in some it was difficult for them to optimize that, and even optimizations around memorization, it was complicated, and the abstraction itself was also complicated. So they no longer exist, but for the definition we saw. But at the same time, I admit it's going to be fascinating, like new work involving that. But the point is, we can think about coroutines and concurrent React. So who here has done any concurrent React features? I don't know, or heard about them? Okay, cool. Should have started with this question. So there's this talk by Dan Abramov from a couple years ago, where basically he was going through some of the things that he envisioned for the future of React. So he had a lot of examples for both network bound operations and CPU bound operations inside components, and that was really interesting, by the way. And he was recreating some really heavy components and how you could optimize that. And I'd like to propose a similar example. So I have this input component, and where it's really performing some huge task as I type, and you can see that you can see the keyboard on the right, and you can see that it gets to a point that I kind of have to wait until I can type the next items, and then it takes a lot of even seconds for me to see what's on the screen, and then after a couple of seconds it even gets to a point that Chrome is gonna crash. And you might be wondering what's the source of that, what's so happy that's happening. So I mimicked this resourceful operation, so I'm iterating up to 1 million just to simulate a CPU bound operation, and then in my component I'm using that. And so here's the next exercise: how could we improve that? Yeah, I'm leaving it for you to think. But I don't have a quiz this time. But let's try to build a scheduler, our own scheduler, with some of the things we saw. And of course, we're not going to do this from scratch. We're going to get some inspiration from the past. So who here has done Redux Saga? Yeah, I know I'm doing a lot of raise your hands thing, but cool. So Redux Saga was like one of the most popular Redux middlewares a couple of years ago, and I myself loved it for a few things, especially the way how it used generators to handle parallelism, concurrency, and other things that come with that, like race conditions and that kind of thing. And keep this thing in mind, the generator thing. So let's go back to our original code and let's make a couple changes. So yeah, a few lines more. And what's changing is we turned the heavy function we had into a generator, and inside this generator, right in the beginning, we are using the execution bug. And like on the bottom, what we're doing is we have this new scheduler object, and we call this perform unit of work method. So of course we're going to discuss the source of that, but let's see how it behaves. So first you can see that it suspends, so the user does see a loading state or something like that. They're not in the dark. And the second thing you can see is that the input field is responsive all the time. So even though I can see still type, and everything happens in a way smooth. And that's the full code for the scheduler we just created, and it's about 40 lines, I guess. But the important part is this performing unit of work, where basically we are switching against 3 different states. So it can be either idle, pending, or done. And the 2 magical things happening here is that first we are throwing promises, because that's kind of how suspense works under the hood, but we're going to discuss this more. And the second thing is that we are using the next method of our iterator so that we can figure out whether this is done or not. And if you've seen some concurrent React stuff, it might sound a lot like the new hook that was introduced in React 18 that is use transition. And if we go back to the original code we had and just rewrite it in terms of transitions, you will realize that yes, what we just did was like use transition, but with our scheduler that we built with coroutines, with the idea of coroutines. And that kind of thing explains a lot about React, because just under the hood, there's no use of WASM or workers or any kind of parallelism for React. What we have though is this cooperative multitasking model, where we have this one single thread, but it's interruptible, and it can be interleaved with other tasks running in the main thread, but also other React tasks like other renders. And that's why, for example, we managed to have the update happening without blocking the one in response to new entry. So it's better if we visualize. So our example was like this. We had the original render task, and then I started typing more. So user input, and because it's user input, it has like high priority. So it had to use and start doing this. After I started typing, after I ended typing, then React, its internal scheduler, could resume the original render task. And one of my favorite things is that it uses the execution back to the main thread every 5 milliseconds. And note that's not a magical number like the ones we have in CSS. It's mostly because it's smaller than a single frame, even when you have like 120 FPS devices. So that's what makes that in practice the rendering thing is interruptible in React. And I know that the example I gave of iterating up to 1 million is not a practical thing. It's not like we're doing this on our jobs. And we have a lot of other non-practical examples that are great for benchmarking, but they're not really applicable on a daily basis. So we have examples like finding primes or cracking passwords with like really heavy algorithms. But what we also have really practical examples. So it's not uncommon that we render apps with a lot of data points, or that we have to render on a canvas and we don't have off-screen canvas, or when we have to process data. So one example of this scheduler thing is this, let's say, a dashboard. So we have records on the right and a timeline on the left, and the thing is, this timeline is supposed to filter the records based on the date. And you can see that it's not great. It's kind of laggy, the animation, and it takes a while. So the user experience is not great. And that's the whole code for it. So we have like user state. We are using user fact to update the data, and we have this dashboard component. So if we use transitions from React 18, just one tiny change of the code. Let's see how it works now. So you can see that it's way smoother, and like filtering happens better. And actually, no matter how wide the range I select is, I still get to properly filter things. And I do have a session, by the way, that's called Deep Diving on Concurrent React, where I talk about more examples and more internals of Concurrent React itself. So if you're interested in diving deeper on that part, that's where you go. But it's also nice that we visualize coroutines out there, like in other parts that's not React. And for that, we can talk about, for example, asynchrony in JavaScript as a language. So we know that asynchronism in JavaScript is what some people call contagious. So if you've migrated one part of your code from a callback-based API to something that is async await, you know that it all starts with one function, but then the function that's on the top level, you also have to rewrite that, and then so on until your whole code now is using async await or promises.then, that kind of thing. And the other thing is that asynchronism is in JavaScript, it isn't free, it's got a cost. So every call we do, we have to allocate callbacks and store them somewhere, and we have to also take a trip back to the event loop to process that. And actually, there's a really good post, it's like from a couple years ago, that's called "What Color is Your Function?" And it's basically addressing this thing of you have to update more and more of your code, but there's a really interesting case that is SASS. So I guess a lot of you have heard of SASS or used SASS. And SASS has two APIs for compiling SASS files. It's got the sync version and the async version. And over the years, the async version became more popular simply because everyone was into promises and async await stuff and etc. And it was even more handy if you wanted to, for example, integrate with Webpack or write loaders, plugins, or any other thing like this. But the thing is, if you were using Node SASS, you couldn't tell the difference in performance because under the hood it was C++ anyways. But for that Dart SASS, because it was turned into JavaScript, it also had to follow JavaScript rules and limitations for async stuff. And the result was that the async version was 2 to 3 times slower than the sync one. And that's when they started using a package called Node Fibers to optimize that and to write the async code, like the async API using the fast sync code. And by the way, Node Fibers is like an amazing package that helped the Node community a lot over the years. And last year it got deprecated because of changes in the internals of V8 and of Node, but it's still got a lot of legacy, and that's interesting to see. So effect handlers. So effect handlers, they're really complex concepts, but one of my favorite definitions is this one, that it's basically a way to reason about computational side effects. And it's grouped by 2 definitions. We have effects that are basically any set of operations, and we have the handlers that basically handle the semantics of and implement how an effect should be. And again, I'm going to go with another language, this time into a language called F. But don't worry, because we'll be using simple examples. So what's happening in these lines is basically first, we have the type annotation. So here we are modeling a user with name and age. And here we define our 2 effects. So we define them with the type signature of what should happen in that effect. And now we can have our effect handlers. So first that you're gonna notice is like some things are similar to the pattern matching thing we saw. And we annotate these with a handler keyword that is part of the language. And as you saw, we have 3 branches here. So the first branch is actually when we have no effect. So here's like our default case, let's say like that. And basically we are just returning a tuple. And the other two cases is actually where we are handling our effects. And you might find like this K thing here weird. So K here is what we call a continuation. So it's basically the rest of the computation that runs after the effect we are performing. And I know this abstraction is really complicated to grasp in the first moment. And thankfully, we have this post by Dan Abramov that's called Algebraic Effects for the Rest of Us. And he provides a really good example using something that is JavaScript-alike. So he has this function that is getName, and now we have this try-handle block. And this is like to mimic as we had an API call to fetch this name. And what we can highlight here are these three parts of the block. And does it sound familiar to you? Like this? Yeah, so it's a lot like throw, try, catch. But instead of throw, we have this perform keyword. Instead of catching an error, we are handling an effect. And this thing we have in the end that in our previous example was the weird K thing is our continuation. So this basically lets us jump back to where we performed that effect. And even though this example is really simple, for me it kind of shows the power of effects, because it doesn't really matter how we hold the state. So it could be like some local store, it could be accessing a database, it could be an API call, or anything that's async. And different from what we saw in promises, we don't have to go bottom up updating the whole code, because with algebraic effects we can simply change how the effect is being handled and we're good to go. And you might be wondering again, what does that have to do with React at all? So we can see a lot of appearances of effects throughout the history of React. And the first of them I know was related to the layout algorithm. So basically they were experimenting a lot in the past of using some data structures that had to do with algebraic effects for managing layout inside apps using React. And again, it's like really interesting documentation for checking out. And then fast forward time, the draft start of the context API. So you've probably heard of the context API or are even using that for handling state. And when they were about to revamp that a couple years ago, they also experimented that with algebraic effects for reimagining how the context API should go. And by the way, another really interesting thing for checking out. And then another example similar to the ones by Dan Abramov, like for handling side effects within a component. So Sebastian Markbach, another core committer of React, he was also experimenting with that a lot like years ago, and he even came up with a similar example, but here instead of fetching information about a person, etc., they were basically fetching theming information, like when you have like a dynamic theme for your app. And again, we see the similar pattern, but instead of throw, we have what he called back then race, and instead of catch, we would have catch effect. And we also have a syntax for continuation. Now we have my two favorite examples, hooks and suspense. So this is like the RFC that introduced hooks. And in this RFC, Sebastian even points that by definition, hooks are algebraic effects. And basically, if we think about the definition, so we know that algebraic effects are a set of operations and a set of handlers for those operations. And here, if we were to make a parallel, the operations would be our hooks. So use state, use effect, and so on. And the difference is that the handlers are inside React. So we don't have to set up the handlers ourselves because they're part of the render cycle. And I think that one good way, for example, is if we forget about one of the rules of the hooks, we're gonna have a runtime error saying that something is not being handled properly, like with the custom message and etc. And that's the same kind of thing that we get in a language like F if we have an effect that's not being handled. And if we think about hooks and effects, we see how React was able to kind of stash from us a lot of responsibility handling this kind of effects and splitting the effects and the rendering, like saving us complexity. I mean, some of people think it's good, some of people think it's bad because it's becoming like a lot of magic inside the framework, but I still think it's a really interesting abstraction. And the next one is the internals of suspense. So I have one or actually two questions. Who here has used suspense, any like the suspense component and etc. Cool. And who here has built an API around suspense that you can, for example, a library or a SDK, I don't know, something that can suspend components. Cool. So basically, if we check libraries that are suspense compatible, like React Fire is one example, you're gonna see that we have hooks throwing promises so that suspense can catch them. And if we start digging into the source code of these APIs, this is React Suspense Fetch, you're gonna see similar blocks of code. They're basically throwing promises. And even React Cache, I think it's like one of the best examples we can check. If we see the source, we're gonna see that basically the same pattern we have. Their component can suspend the fiber it is running in by throwing a promise. And the first time I saw that, it sounded like a really hacky solution. I was like, I could be doing that. So where are they doing that? But basically, if we think more about the abstraction and about what we saw for effect handlers, basically it's the throw, handle, resume pattern that we have from effect handlers. So it's really an abstraction inspiration. And by the way, before we move forward, you heard about F, but actually effect handlers are in a lot of other contexts. So besides the F language I showed, there's also Coca, that is another language for modeling things around algebraic effects. And even OCaml is for sure more popular than these two. And the multi-core module of OCaml, it is also modeled around algebraic effects. Last but not least, continuations. So I love the explanation that the Smalltalk documentation had for continuations, because they kind of compared that with go-to instructions. So basically, it's at my heart, I am something like a go-to instruction. My creation sets the label, and my methods do the job. However, this is a really powerful kind of go-to instruction. And I know it's scary to hear about go-to, and it feels like, okay, we've gone past this decades ago, right? But basically, a continuation is an abstraction, as we saw in the effect handlers, that represent the remaining steps in the computation. And it's nothing but a control flow primitive like ifs, elses, while loops, and etc. But the difference from goto is that one of the most harmful things about goto is that we lose context when going to things. But in continuations, we have variables, we have pointers, and we have all the context. And they enable us to do a lot of things. And the React team is aware of that, so they've been shown through a lot in previous steps in React and etc. And they even got examples of that. And one of my favorite ones is this function. It's called perform work, and it's like a simpler version of some part of the reconciler that we have. And you notice this while loop. So what we're doing here in this function is we are handling a queue of tasks or of fibers, in this case, to be processed. And basically, if there are still tasks in this queue, it's going to continue with the perform work function, and then it's going to be scheduled for later. So in this context, we can say, for example, that this function perform work was heavily inspired by the idea of continuation, even though it wasn't implemented using continuations. And actually, we can see continuations a lot on the web as well. So we have this API that is the main thread scheduling API, and it's got like Uding utilities and a lot of stuff, and it's heavily inspired by continuations. And there are even really good examples for that we can combine parts of this API, like the isInput pending thing and the scheduler.ut. And we can, for example, use execution back to the event loop, and then we can detect if there's any input pending to be processed. And if not, we can continue processing that. And yeah, I would definitely recommend that you check out this whole new scheduler API. Some parts of it are implemented already, and people are actually using that in production. And continuations are actually famous in other languages. So, for example, Smalltalk, which is a language that inspired a lot JavaScript and also inspired a lot object programming in general. They have a framework called Seaside, and that's basically a web framework. And yeah, I know it's a bit weird, but it's heavily inspired by the idea of continuations, and they have continuations at the core. So, a few closing notes of all of these concepts and crazy ideas that we saw. I would say that first, recapping, Fiber was this rewrite that happened years ago, and that enabled suspense, concurrent React, and a lot of things. And basically, the key idea was to give more low-level control over using and overall over the execution of the things. And in this model, we have fibers as this primitive to model execution in a comparative way, and effect and algebraic effects as an inspiration for handling effects in a scenario where their behavior was independent, as we saw with the things with hooks. The second thing I think we can notice a lot is that React tries to overcome or to address the lack of some features that other languages have or other platforms and the JavaScript or the web don't have, with their own alternative solutions. So the thing of throwing promises, for example, the first time I saw that, I was like, I had a bit of imposter thing. I was like, I could be doing. I actually had the opposite. I was like, I could be doing that. So why is the React team throwing promises and etc.? But once you get a better grasp of the abstraction around that, you see that okay, JavaScript they wanted to do algebraic effects here, and JavaScript as a language doesn't have it. So that was one of the possible ways, and that's the same thing with continuation and etc. Another thing I think is that understanding some of these concepts, they help us getting the mental model behind those things. So there's still posts nowadays that they address or they try to address the problems of how hooks were introduced. Because when hooks were introduced, the only model we had for getting the idea was to compare that with lifecycle components, and that led us to a lot of problems and a lot of code that was trying to mimic life cycle of the class components, but when hooks are not supposed to be that. So if we start learning hooks by getting the idea of them, okay, so these are effect handlers, this is what some languages do, this is what hooks are trying to do here. So I think that helps a lot understanding some things. Also, understanding these internals and the motivations behind them helps us writing our own abstractions. So it was the example with the coroutines-based scheduler that actually there are APIs out there using that kind of thing, using generators, for example, to offer good scheduling solutions, or the thing with pattern matching components. So that pattern matching thing was really helpful for me in scenarios where I had to match the shape of objects and conditionally render, and I had like huge if analysis or switch statements or etc. For the next conclusion, I'd like to mention this tweet by Shep Hosh. He's the CEO of Verso, or back then Zeit, and he said that React is such a good idea that we would spend the rest of the decade exploring the implications and applications of React. And I couldn't agree more. I think that the fact that we're here discussing all of these crazy concepts and things that we would probably even skip in the CS classes, and how they all relate to React or even to front-end the web platform, I think it shows that React is this democratic agent for this kind of concept, and I think that's basically pushing us and even pushing other platforms to learn about that or to use that. A picture is worth 1,000 words. So for the next conclusion, I have this picture. This was me about 8 or 9 years ago in an iOS developers meetup. And I was just basically telling them that Angular would be the future and that they should move to Ionic and all these things. And yeah, this was supposed to be fun. So I guess another closing note would be, don't always trust all of my speculations or future predictions or ideas around the web. It's not a conclusion, but it's a closing note. We are hiring a lot at Medallia. So if you're interested in working with a platform that has like a huge scale and has interesting performance challenges, reach out. The slides for this session that you just saw are available already on my speaker deck profile. So if you missed some links from the previous slides, or if you want to catch up with all the links, you can just find all the QR codes over there. Yeah, it's always tricky to move from this slide because if you missed the previous slide, I also got this one unique link that is where you have like things about working in Medallia, but also other sessions. So if you like things about performance or deep dives into frameworks and that kind of stuff, you can also find them over there. As always, it is a tradition for me to have stickers everywhere I go. So if you want stickers, just reach out, like share your experiences or your thoughts or questions, feedback, whatever. And that's pretty much I had for today. Yeah, if you want, we can chat, like I'll be over the event, etc. So thank you all for having me.